Good afternoon, ladies and gentlemen, and welcome back to this fourth and final session of the 14th Concawe Symposium. We are delighted to welcome you here in Brussels. I am Alain Mathurin, Communication Director for the Association, and I'll be moderating this last session. Before I start with the session itself, may I remind you that you will be able to interact with our speakers. To that extent, you have access to a chat box on the right side of your screen. Type your message, choose to be anonymous or put your name, click on the send button, and I will have it on my iPad. You will also be able to follow complimentary information, especially in the coming days, through our LinkedIn page. I also invite you to connect and follow us on our LinkedIn page. And with this, I will now be able to continue with our presentation of the four speakers of this fourth session. Alternative fuels towards 2050. We have four experts that will walk us through the different aspects of those alternative fuels, starting with Robert McCormick from National Renewable Energy Laboratory. Good morning, Robert. It's quite early for you. Thanks for calling in from the US at 7 in the morning. Our second speaker will be Roland Dauphin from Concawe. Roland is with me in the studio here in Brussels. Welcome, Roland. Our third speaker is Calliope Panoutsou from London Imperial College and calling in from London. And our fourth and final speaker is Bouter from IFPEN, calling from Paris. Good afternoon. Welcome to all of you, and let's start with our first speaker for this session, Robert McCormick. Quick introduction, Robert. Dr. Robert McCormick has a PhD in chemical engineering, senior research fellow in the Fuels and Combustion Science Group at the National Renewable Energy Laboratory. This group's research is focused on biofuels properties and fuel engine interactions, including biofuel quality and quality specifications, compatibility with modern engines, combustion chemistry, pollutant emission effects, and leveraging fuel properties for design of more efficient engines. I will stop it here. You can find the full bios in the program that you have received in your emails. Robert, the floor is yours.
Well, thank you for the kind introduction and for the opportunity to be here today to talk about our work on alternative fuels development for diesel engines. This work was part of a large 6-year effort at multiple U.S. Department of Energy national laboratories called Co-Optimization of Fuels and Engines. I come from the National Renewable Energy Laboratory, which is one of those Department of Energy labs. And if the sun was up, it would be a beautiful morning just like this here in Colorado. The idea behind co-optimization of fuels and engines, or what we refer to as co-optima, is to work together on both fuels and engine technologies at the same time to try to get to a point of being able to introduce better fuels and better vehicles sooner. But this was done at a foundational research level in the sense that we're not developing prototype engines or vehicles, but we're working at a more fundamental level. The program as a whole over 6 years focused in the early years on light-duty vehicles and fuels, which in the United States is, of course, spark ignition engines. And then in the second 3-year section of the 6-year program, focused on fuels and engines for heavy-duty and medium-duty applications. And what I'll talk about today is our work relevant to conventional and somewhat modified diesel combustion with diesel-like fuels. Looking at the program's outcomes from a very top level for everything, you can see that we were quite successful at demonstrating the potential to significantly improve the efficiency of light-duty engines using engine designs that were optimized for fuels having the right properties. The work that I'll speak about in the rest of my presentation will be on medium and heavy duty fuels, where we've identified a number of different blend stocks that have performance advantages as well as significantly reduced life cycle greenhouse gas emissions. And we've also identified a potentially lower cost path to reduce engine out and criteria pollutant emissions. So the whole idea of Co-Optima, whether it's light duty or heavy duty, has been to focus on the concept that equivalent fuel properties result in equivalent performance regardless of the fuel chemistry. But of course, we have to pay attention to the fuel chemistry because the people who are trying to make the fuels are working at a molecular scale level. And we've spent quite a bit of time developing molecular structure property relationships and trying to understand how fuel chemistry affects properties. But when it comes to engine performance, we've focused on fuel properties. For diesel fuels, I think anyone who works on diesel fuels will be quite familiar with the list of properties that I have here. The fuel has to rapidly ignite. It needs to completely vaporize. Cold weather operability can be an issue for diesel fuels, so we need fuels with a low freezing point or a low cloud point. Fuel pump and injector operability or durability is a critical feature. Fuel has to be handled safely, and then stability and storage can be a significant issue for certain fuels. Our approach to identifying fuels was looking in the literature, looking to biofuels researchers. We came up with on the order of 1,000 potential biofuels, which were then screened based on their properties. At a very high level, the tier 1 screening was just, can it be a fuel? Does it boil in the right boiling range to be a diesel fuel? Does it have a high enough cetane number and other properties? For some of these materials, the properties were just predicted. We didn't have any volume of the material. At the next level, we tried to measure properties that had been predicted, and Co-Optima has been a blending strategy where we're focused on blends and petroleum-derived fuel of up to about 30 volume percent. So really, in some ways, a transitional strategy from where we are today to where we need to be by 2050. So obtaining the blend properties was important in the second tier. And then in the third tier, we're actually evaluating fuels and engines, looking at well-to-wheels greenhouse gas emissions, and performing techno-economic analysis regarding the fuel production. So here's the outcome of a lot of that effort. 13 blend stocks that have at least the potential to reduce greenhouse gas emissions significantly. They have good fuel properties and potential to be produced at larger scale for those that are not produced from fats and oils. We have the fats and oils produced fuels, biodiesel and hydrocarbon renewable diesel on this list, but the other fuels are generally produced from larger scale available biomass feedstocks. In terms of entering the market, the hydrocarbon fuels, of course, have the lowest barriers. There's a set of ester fuels. There are esters on the market today, so there would be more barriers to putting these on the market than the hydrocarbons. But the ones with the highest barriers entering the market are the ethers, which have not generally been used in commercial diesel fuels. Potentially, some of these would require storage stability additives, and an assessment of toxicity and biodegradation is critically important, and that's ongoing and should be available in the next few months. So in order to analyze the environmental impacts and the potential costs, we've used the Argonne National Laboratory's GREET model, and then coupled that with techno-economic analysis, essentially a top-level process design that gives us energy inputs to make the fuel. And then the techno-economic analysis itself gives us a modeled fuel selling price that we can compare. Looking at some of those results, here I show the life cycle greenhouse gas emissions in this bar chart. Some fuels get some greenhouse gas emission credit. So the net carbon intensity in grams of CO2 equivalent per megajoule is the black dot on the bar. Petroleum fuels are well above 90 grams of CO2 per megajoule. And you can see that many of our fuels are below the 60% reduction level that has regulatory significance in the United States. And quite a few of them are even lower. And if you were to, I know you probably can't see this chart very well, but if you were to look at it in detail, you would see that sometimes the fuel's on here a couple of times with different feedstocks, because the feedstock can have a really huge impact on life cycle carbon intensity. In terms of minimum fuel selling price, we talk about this in terms of unfavorable, neutral, and favorable. Whenever we put dollars on here, we seem to generate more controversy than it's worth. And perhaps this highlights the approximate nature of the analysis, in that the designs we're using are really top level and not highly detailed. Reducing costs is a key challenge for most of these fuels. There's a few that have modeled selling prices that are barely in the favorable range, and that's because they come from extremely inexpensive feedstocks, such as wet waste. I'll go into just a couple of details. Here we have an example of hydrothermal liquefaction, where one could do it from wet waste with a water treatment as the first step, or from algae, which eliminates that step, or from woody biomass more directly. The woody biomass has higher greenhouse gas emissions in its production and higher costs. But if we look over here on the right for the algae case, we're just barely meeting our greenhouse gas emission reduction target of 60% with costs in the neutral range. But if we use the very inexpensive wet waste feedstock, we can get significantly lower greenhouse gas emissions and have a modeled cost that's starting to look more reasonable. The other example I'll show is isoalkanes made from volatile fatty acids. If you start from biomass, you have on the top, you have a fairly complex process, but if you start from very inexpensive food waste, you have a lot fewer boxes in the flow chart. From a biomass feedstock called corn stover, we're unable to achieve our greenhouse gas emission reduction targets with this feedstock, and model costs are high. But if we use the food waste, which is of course not available in anywhere near the same quantity as corn stover, we can, depending on how you allocate, achieve significant greenhouse gas emissions or even very large greenhouse gas emissions, and model costs are starting to look more favorable. The next aspect is moving into examining these fuels and engines. I'll show you some data that were acquired in a single cylinder research engine that was built to be exactly the same as a commercial medium duty engine produced by Ford. As a single cylinder engine, we have control over all the engine operational parameters, as opposed to testing it in these fuels in a actual commercial engine in a vehicle where the manufacturer's computer would control the engine operation. We tested these as 30% blends, and so the list of fuels is here. These are fuels from the previous list, or in some cases surrogates for them. By that I mean similar molecules that we could obtain in the tens of liters quantity that's required for engine emission testing. The chart here is a NOx soot trade-off chart where we show NOx emissions on the x-axis and soot emissions on the y-axis. And we're doing a sweep of exhaust gas recirculation. We're out here on the right at 5 grams per kilowatt hour of NOx, we're about 25% EGR rate, and then we increase EGR, which reduces NOx, but at some point causes soot to go back up. And the black line at the top is the conventional petroleum-derived fuel. The next group are the hydrocarbon biofuels, and then we move into the oxygenates. You're able to go to higher EGR rates without seeing a spike in soot emissions. And then for the polyoxymethylene ethers, which are the purple line at the bottom, it's very difficult to get this material to make soot, so it can tolerate very high levels of EGR, achieving quite low NOx emissions. But while these results are good, nevertheless, they're not big enough reductions to really change the design or the size of the diesel emission control system that we use on heavy duty engines today. So we looked to engine combustion changes to try to achieve lower emission levels. My colleague at Sandia National Laboratories has developed an approach called ducted fuel injection that is motivated by a Bunsen burner concept. If you look at the Bunsen burner on the right, the fuel is injected through the nozzle in the center into a tube or a duct, and this causes a lot of air to be entrained from the holes in the bottom of the burner. You can actually do the same thing in a diesel engine. This photograph is a high-speed photograph taken from a single-cylinder diesel engine that has an optical window in the cylinder. And so in the piston, looking up through the piston to the engine head, where we can see on the left, it's a 2-hole fuel injector, and the injector on the left is conventional diesel combustion. And you can see the diesel spray, and you can see the bright yellow and orange, which is incandescence from hot soot. But the injector on the right is equipped with a duct, and for that injector, we don't see any incandescence from hot soot. We see only a blue flame, indicating that the vast majority of this soot has been eliminated by injecting the fuel to the duct and dramatically increasing the amount of air that's mixed with the fuel spray. This is another NOx soot trade-off curve. The black line and then the red box shows the current US EPA on-road limits for heavy-duty diesel engines. Using ducted fuel injection, we're able to get, for this engine at these conditions, the soot emissions down to the regulated level. And then we're able to use exhaust gas recirculation to push NOx emissions down into the box without increasing soot emissions. The ducted fuel injection is highly tolerant of exhaust gas recirculation. Here, this was done by just adding nitrogen to the intake air to simulate exhaust gas recirculation. And this is at a relatively low engine load, and it's at steady state conditions, and it's a 2-hole fuel injector. So this is sort of a concept demonstration that really needs to be taken to another level to actually show that it could work in a real heavy-duty truck engine. Many of the fuels that I showed on earlier slides were oxygenates, and DFI is synergistic with oxygenates. The bar chart here, the 2 bars are for the pairs of bars. One is for no EGR, and one is for significant level of EGR. The brownish bars show results without ducted fuel injection. Using the ducted fuel injection, we lowered the soot by about a factor of 10. Then by blending an oxygenate into the fuel, we can get a further factor of 10 reduction for a total factor of 100 reduction in soot. And so this all, at the same time, we can use pretty high levels of exhaust gas recirculation to reduce NOx. So this may be a large enough reduction that we can reduce the size and operating cost of the diesel emission control system on the engine. So just quickly summarizing, we've identified blend stocks with relatively low carbon emissions and meeting diesel property requirements that have reasonable production pathways from various forms of biomass, and also identified potentially lower cost path to reduced engine out emissions via ducted fuel injection. To take Cooptima to the next level, to really fully realize its potential, there are a number of recommendations we have. One is, of course, to continue to work to reduce fuel carbon intensity by understanding what are all the factors that cause fossil carbon emissions and how we can eliminate them. Working to achieve higher fuel blending levels, 30% is very much an interim sort of level, and how can we expand that to ultimately get up to 100% low net carbon fuel. Working to scale up the production processes, ultimately to commercial scale. But in many cases, we just need to get scaled up to the point where we can make enough fuel for a really detailed evaluation. And of course, continuing to improve our pollutant emissions profile. And so where the Department of Energy is going with work in this area is going to be to working on large, hard to electrify vehicles, definitely aviation, large marine vessels, and rail, and with a de-emphasis on fuels and combustion for light-duty vehicles, and maybe even an elimination of focus on work on fuels and combustion for light-duty vehicles, and a de-emphasis for work on road heavy-duty vehicles. And so with that, I'd like to thank the sponsors of this work, which were the U.S. Department of Energy, Office of Energy Efficiency and Renewable Energy, Bioenergy Technologies, and Vehicle Technologies offices. These links will take you to some additional information about Cooptima, as well as to our publications database. We've published over 300 reports and papers during Cooptima. I suspect there's another 100 that will come out in the next year. And with that, I'd be happy to try to answer any questions.
Thank you very much, Robert. Great to hear this research and the results here. A first question that is regarding the emission reduction. Considering the huge improvement made in reducing diesel engine emissions with the use of engine and after-treatment technologies, do you still consider that fuel effects on engine out emissions are impactful?
Certainly, there's been a time when I was of the opinion that fuel effects on engine out emissions really didn't have an effect on tailpipe emissions because of the success of diesel engine emission controls. But I think with ducted fuel injection, we see that if you use an oxygenated fuel combined with ducted fuel injection, you can get such a large soot emission reduction and a large NOx emission reduction that you could potentially maybe not achieve lower emissions, but achieve those emissions at a much lower cost. And that would be by reducing the size of the SCR catalyst, by reducing the urea required, the diesel exhaust fluid required to reduce the NOx. And we have an analysis suggesting that those reductions are worth thousands of dollars a year to a truck owner. And then potentially combined with low ash lubricant, the reduction in soot emissions could allow both a reduction in the size of the diesel particle filter and also significantly reduce its average back pressure, which impacts fuel economy over the life of a vehicle. We haven't actually done an analysis of that yet, but it seems like it could be a significant benefit as well.
Thank you. I have your question here. There's no signature. It's an anonymous question. What is the process maturity for the proposed barrier fuel compounds, esters and ethers? What would you consider to be their production and industrialization timeframe?
For the esters and ethers, I mean, the conventional biodiesel is produced on a fairly large scale globally. So I would say that technology is at a commercial level with ASTM standards and SIN standards that are well established. For that process, I think it's ready to go now. But of course, it is a feedstock that is somewhat limited. You're not going to replace all the diesel fuel in the United States or anywhere with fats and oils derived fuels.
Just final conclusion, question, sorry. These will all be drop-in fuels?
Certainly the hydrocarbons will be drop-in fuels. It's not clear for the oxygenates to what extent they can be drop-in fuels. They may be drop-in fuels at some blend level, but can we push them to 100% as a drop-in fuel? I think that's to be determined.
Thank you for that. We'll come back to you at the panel in about 1.5 hours. Thank you very much, Robert. Let's now turn to our next speaker. Next to me here in the studio, Roland Dauphin. Before I give you the floor, and I already hand you the slide changer, there we go. Roland is Science Executive for Fuels Quality and Emissions at Concawe. He holds an MS from the École Polytechnique in Paris, an MS in Engine Engineering at IFP School. He started at IFP Énergie Nouvelle in engine technology and became project leader in fuel engine matching. 2016, you joined Total as a fuel scientist where you developed racing fuels and biofuels. You also provide courses on engines and fuels at IFP School. Since 2019, you coordinate a research program in the field of fuels quality and emissions at Concawe, and you co-chair ERTRAC's Energy and Environment Working Group. And this is exactly the organization that you are looking at its roadmap now.
Exactly. Good afternoon, everyone. And indeed, today I will be speaking on behalf of ERTRAC, and I'm happy to share with you an update on our roadmap on sustainable energies and powertrains for road transport. This is a document which is coordinated with my two colleagues from ERTRAC, Simon Edwards from Ricardo and Michael Weissner from Volkswagen. Here is the outline of my presentation. After the introduction to the purpose of the roadmap, I will focus on two of its chapters, the first one on energy carriers and the second one on well-to-wheel assessments before concluding. So first, a quick word about what is ERTRAC. ERTRAC is the European Road Transport Research Advisory Council, and it gathers the main stakeholders of the road industry. It gathers the automotive industry with the suppliers, the fuel and energy suppliers, the managers of the infrastructures. We also have the users, the representative of the cities, the national bodies, and the EU regulating authorities. And the European Commission is also, of course, present. And we also have the research providers because we are dealing with research here. ERTRAC is recognized and funded by the European Commission, and on the right-hand side, you can see the numerous contributors to this roadmap, which allows to have quite a broad overview of the global road transport in this roadmap, and I thank all of them for their precious contribution. So the purpose of this roadmap is to provide an up-to-date perspective on renewable energies and powertrains, options for road transport, and the goal is to provide R&D recommendations for European research programs and partnerships. Previously, we had 3 different roadmaps on energy carriers, internal combustion engines, and electrifications, and we decided that it no longer makes sense to consider them separately, and it's much better to merge them to consider road transport as a global issue. So this is what we have done here, and the target is to reach carbon neutrality by 2050, so net zero CO2 emissions, on a well-to-wheel perimeter and even LCA when the data is available. By the way, we have also considered pollutant emissions for air quality issues in our roadmap. The scope is to understand what is the current status of the different technologies regarding energy carriers and powertrains, and how this technology can develop and can be rolled out, and what it would require in terms of development of infrastructure to allow this technologies to work together. We have also considered different scenarios for putting the different pieces of the puzzle together with a systemic view, and we have provided insights on the research needs regarding road transport research needs for the decades to come. Here is the structure of the roadmap that we are currently drafting. It is expected to be released early 2022, so in a few months from now. There are 3 very technical chapters on energy carriers, powertrains, and infrastructures. Then we have a 5th chapter on systemic view and use cases, and finally the research recommendations. Today, I will focus on 2 chapters on energy carriers and scenario design. So let's first start with the energy carriers, and first we need to define what is an energy carrier for road transport. Probably you all have in mind that an energy carrier is not an energy source in itself. Only primary energies can be energy sources in themselves. But the energy carriers simply carry the energy from the primary source to the final use, which is road transport in this instance. What is important to have in mind is that whatever energy carrier you consider, you will have 3 universal steps that characterize them. First, there are primary energies, and then they go through processes before they become energy carriers. And at each of these steps, you have properties which characterize them. For example, for the feedstock, they can be more or less available, more or less costly. You will have different carbon intensities. They can have more or less impact on biodiversity and so on. Regarding the processes, the technical maturity is an important issue. The cost, once more, is important. The yield of production, so the difference between the energy that you will put at the input and the energy that you will get at the output is important. The generation of waste is also an important matter, and so on. And finally, the energy carrier can be more or less suitable for transport in terms of ability to be transported, to be stored, its energy density, and of course, at the end of the day, its cost. When reviewing all the different existing energy carriers and the ones that can be foreseen, it's quite easy to see that there is no existing single energy carrier that has the best-in-class properties at each of these 3 different steps. At each time, you have relative pros and cons, depending on the needs of the specific transport that you are considering, which basically means, and I know that it is an idiomatic expression now, but there is no silver bullet because, in fact, you have always benefits and drawbacks for each of the energy carriers that you may consider. We have grouped the energy carriers in 3 different categories: electricity, liquid fuels, and gaseous fuels. So let me start with electricity first. Our central scenario is the 1.5 tech scenario from the European Commission in their report Clean Planet for All. In this scenario, the electricity would represent more than 50% of the final energy use by 2050 compared to less than 25% today. In order to do this, the installed capacity would be multiplied by roughly 3, which is, of course, a huge increase. And by 2050, the electricity mix would be mostly renewable. 83% of the generation capacity would be renewable, mostly relying on wind and solar energy. But it's not 100% renewable for this mix. You still have a small share of non-renewable sources with nuclear power plants, 12%, and natural gas using carbon capture and storage, 4%. If you consider the whole electricity mix with carbon capture and storage, it generates net negative CO2 emissions overall. Additionally, as a sensitivity case, we have also considered 100% renewable electricity mixed in order to compare what would be the different outcomes. Our main messages regarding electricity is that there would be a change of paradigm in the future. Today, you produce electricity on a real-time basis to address the demand. In the future, it will be more about grid balancing between a demand that would be flexible with cooperation between users and system operators to cope with what is produced with the intermittent system. In order to balance as a grid, you also need grid interconnections between the countries, between the regions, and also the development of new storage capacities. Today it's mainly pumped hydro, but in the future you need also to develop other ways to store electricity with batteries or with hydrogen for seasonal storage. Now moving on to liquid fuels, we have two main categories, and they have been mentioned quite extensively yesterday in session 1 and 2. We have biofuels and e-fuels. So regarding biofuels first, of course the stake here is to move away from biofuels made from food and feed crops to more sustainable biofuels using more sustainable feedstock. The different processes allowing to produce these biofuels are detailed in the roadmap. It has been also detailed yesterday. I won't spend too much time on that for the sake of time. But what is important in terms of message in our roadmap is that biofuels are not an alternative to electricity. They are a complement because both of them complement each other very well. And especially with biofuels, which can be used in many different sectors, they fit well with passenger cars, heavy duty, maritime, or aviation. Regarding e-fuels, probably know that they can be made out of renewable hydrogen and CO2 capture. They can consist in, chemically speaking, very different compounds. Some of them can be drop-in, some others not. But the real trouble with e-fuels is that thermodynamically speaking, they are very inefficient to produce. And once you put them into an internal combustion engine, you have another stage of inefficiency, which means that the overall well-to-wheel efficiency of e-fuels is very low. And it's very low if you compare that versus against direct electrification. For this reason, we really want to allocate in our roadmap the e-fuels to the hard-to-abate sectors, such as heavy-duty, long transport, heavy-duty, maritime, and aviation. Moving on to gaseous fuels, you will find information about biogas in our roadmap. Biogas is considered for one of our scenarios in heavy duty, where liquefied biomethane could be used. We have not considered liquefied biomethane in maritime, just because maritime is out of our scope. We just focus on road transport. And of course, we have considered hydrogen, whether it is made of green hydrogen, renewable electricity, or blue hydrogen made from steam methane reforming with carbon capture and storage. An important message here is that hydrogen would play a central role in the future energy system if this energy system has to be carbon neutral. It's not necessarily a matter of quantity, but it's a matter of integration of the global energy system, because hydrogen can be used. We have seen that for balancing the grid system. It is necessary for seasonal storage. We also know that it can be an energy carrier, can be used in a fuel cell, for instance. Or if you want to produce e-fuels, it is also an intermediate chemical feedstock. And so hydrogen could be virtually everywhere in the energy system to integrate the different parts of the energy system together. So now moving on to the second part of my presentation on well-to-wheel evaluations. In this study, we have considered, well, we have designed 48 different scenarios. I'm going to explain how they have been designed. And the goal in designing all of these scenarios was to make all of them carbon neutral. And the question that we asked is what it would take in terms of well-to-wheel energy demand, in terms of electricity demand, in terms of requirements regarding carbon capture and storage, and so on, in terms of biomass needs, for instance, what it would take to make all of them carbon neutral. So the 48 scenarios have been designed with a combination of the 4 different categories that you can see here. We have considered different powertrain scenarios and different fuel scenarios. I'm going to detail them in the next few slides. And also 2 different electricity scenarios, the 2 ones that I've just detailed, the 1.5 tech and 100% renewable scenario. And we have considered optimistic and pessimistic ranges regarding the primary energy demand, depending on the technology improvements regarding the efficiency of the powertrains, and also regarding the improvement regarding traffic management and traffic reduction measures. So let me detail the powertrain scenarios. So you see that I've considered 3 of them. On the left-hand side, you have the highly electrified scenario, relying on a lot of BEVs and PHEVs. Then in the middle, you have the highly electrified with hydrogen scenario. And on the right-hand side, you have the hybrid scenario, which relies more on the use of internal combustion engine. For each of these scenarios, we have considered a different fleet mix for each of the vehicles category. On the left-hand side, you will have the small vehicles category, 2-wheelers, small passenger cars. And moving on to the right-hand side, you will find long-distance transportation up to heavy-duty trucks. In the highly electrified scenario, you see that there is still a share of plug-in hybrid electric vehicles. You have to know that in this case, these vehicles are highly electrified. They are driven between 70% and 90% of the time in electric mode. You can also see that for heavy-duty trucks, they rely on electrification either by using battery electric vehicles or electrified road system. For the scenario using hydrogen, the use of hydrogen is done through fuel cells and is dedicated to long-distance transports. The last scenario that we have named hybrid is a scenario in which we have considered that maybe the infrastructure regarding electricity or hydrogen would not be deployed fast enough for the 2 other scenarios, and so we would still need to use the existing infrastructure with internal combustion engines and liquid fuels. So now some details about the fuel scenarios. You can see that we have a scenario relying a lot on biofuels, up to 90% of the liquid fuels. Another one relying a lot on e-fuels, up to 100% of the liquid fuels. A scenario which is mixed, which is really in the middle. And even a scenario which has a limited fossil content, only 10%, but just to check what it would take in terms of compensation measures if ever we don't manage to get rid of fossil fuels by 2050. In order to do our evaluation, we have simulated an energy system, and you can see in this picture the scheme of this energy system. It's quite complex. So just in order to try to simplify it, you will find once again the 3 steps between energy carriers and primary energies. On the left-hand side, you have the primary energies. It can be biomass, waste, wind, solar, fossil resources, if they can be used. And on the right-hand side, you have the energy carriers, which are either direct electricity to the vehicles, liquid fuels, biofuels and e-fuels, or hydrogen, or even fossil fuels. And in the middle, you have the processes which transform the primary energies to energy carriers. And you have one masterpiece in these processes, which is the electricity generation. Electricity is used virtually everywhere, of course, to feed the vehicle with direct electricity, but also to produce hydrogen, which is necessary to produce e-fuels, and also you need electricity to produce the biofuels. So this is really important to care about this particular piece of the energy system. Because even if you get rid of fossil fuels, this energy system is not completely carbon neutral. You need offsetting measures to compensate for the remaining CO2 emissions. And this is the purpose of this green box that you can see in the middle of the energy system, which are the negative CO2 emissions that you can generate, for instance, by using bioenergy, carbon capture, and storage. So now are the results of the simulations. You can see here the results of the evaluations of the 48 scenarios here in terms of well-to-wheel energy demand. When I'm saying well-to-wheel energy demand, it means that we have considered the energy that would be lost in producing the energy carriers, the energy that is consumed on board when you drive your vehicle, but also the energy which is required, for example, to capture CO2 and put it underground, or to use it for producing e-fuels. What is interesting is to compare the different scenarios in order to understand which are the parameters that play a great role in your energy system design. An important conclusion in this analysis is that if you want to rely a lot on e-fuels with internal combustion engine, it is almost mandatory, it is of the highest importance, to get 100% renewable electricity, because if you don't have that, the well-to-wheel energy demand will literally skyrocket and reach levels which are not reasonable. So the conclusion of that is that for e-fuels, it is mandatory to get 100% renewable electricity. Another important conclusion is that the well-to-wheel energy demand depends a lot on the fleet composition. And here the conclusion is very clear. The more you go towards electrification, the lower your well-to-wheel energy demand. The difference between the scenario is absolutely huge, up to 3,000 terawatt-hour. It is a huge number. And it is allowed because electrification allows to work with much higher well-to-wheel energy efficiency. The second parameter which is important is the difference between the optimistic and pessimistic ranges, which are allowed by technology improvements or traffic management technologies. This can have a huge impact on the well-to-wheel energy demand, and it means that we have to pursue R&D efforts to reduce this energy demand, and also to work on traffic conditions to reduce the overall demand. And the final conclusion is that the way you will produce your liquid fuels also impacts by huge factors the overall well-to-wheel energy demand. If you produce your fuels by using biofuel processes, you will require far less energy compared to e-fuel production, simply because when you produce biofuels, you let Mother Nature produce the biomass, and that's an effort that you have to do less by yourself to produce this energy. So another question was about the electricity demand. You remember that electricity generation is at the core of the future energy system, and how much electricity you would need in this future energy system, how much electricity you need to generate. And here the range is really huge. In fact, the range is between 20% of today's electricity demand and up to 160% of today's electricity demand. The lowest range, 20%, is still very significant, but the lowest range is reached in scenarios where you rely a lot on internal combustion engines and biofuels. This is where you need the least amount of electrification. At the other hand of the spectrum, you have still internal combustion engines, but this time fed with e-fuels. And this is where you reach this amount of 160% of today's electricity demand in Europe. And of course, this is a huge number, which has to be I remind it 100% renewable, and you may wonder if it's reasonable to consider such a high amount of renewable electricity by 2050 only for road transport. In the middle, and rather towards the lower end, you have the highly electrified scenarios, which require between 40 and 55% of today's electricity demand, which is still, as you may consider, very significant. So some conclusions to finish my presentation. We have seen that developing a carbon neutral road transport is something which is very, very, very complex, and even which beyond the well-to-wheel evaluations, which are far from being simple. There are other parameters which must be considered. The scalability must be granted. It means that the critical minerals have to be available to allow to move on with the renewable system. If you consider biofuels, biomass must be available, water supply must be ensured, and so on. Because we will rely on intermittent renewable energy sources, it is important to ensure that energy supply is secured at any time. And it means we have seen that cooperation between, flexible demand, cooperation between the users, and also storage. Customer acceptance is key because you won't manage any transition without the customer. And in the end, we see that we need a systemic evaluation to ensure that the whole system is viable. And it really means to care about every detail, because it is enough to miss just one of these details to have a failure of your whole system. For example, if you don't have the critical minerals, you cannot succeed in electrification. If you don't have biomass, you cannot succeed in biofuel production, and so on and so on. So every detail is very important, and of course, it generates uncertainty. Beyond this uncertainty, we have some firm conclusions. We see that to achieve carbon neutral transport, we need drastic changes in 3 different areas: powertrain technologies and vehicle technologies, traffic management, infrastructure development, and also in terms of energy production, whether they are electricity, liquid, or gaseous energy carriers. We also see that electrification will be everywhere, whether you consider battery electric vehicles, possibly combined with electrified road system, plug-in hybrid electric vehicles, or fuel cell electric vehicles. This electrification is necessary because it decreases well-to-wheel energy demand, which may be scarce in the future. And another thing which is important is to decrease energy demand at the source by using energy measures, energy efficiency measures, either through technology or traffic conditions management. Regarding the demand on energy carriers, it is expected to decrease by a huge factor for liquid fuels, between 50% and 95% for liquid fuels, depending on the scenarios. And on the other hand, the demand for electricity will increase, and the range of uncertainty, depending on the scenario, is huge, even if the high-end scenario seems quite unlikely. Before you electrify everything, you need to ensure that you have a carbon-neutral production of electricity, otherwise you will just displace the CO2 emissions from the tailpipe to somewhere else. And finally, we have seen that hydrogen is a masterpiece of the future energy system, because it will really integrate the different pieces of the energy system together. I would like to, before finishing my presentation, I would like to thank all the participants of the ERTRAC CO2 evaluation group, and especially Marta, Hugo, and Jette Krause. And I thank you for your attention.
Thank you very much, Roland. Quite surprising in some ways. Just one question, because we have to manage the time. I understand that you see in this study a huge potential for also electrifying the entire heavy-duty fleet. This is the way I understand that. From a technology perspective, how will you be able to achieve that?
This kind of scenario is allowed by the fact that we have many stakeholders in the ERTRAC community. And one of the stakeholders have brought the technology of electrified road system, which can be, well, achieved by several technologies. Well, the one which is the most known technology is by using electric lines over the roads. And it is a technology that could be brought progressively, first by electrifying the highways, and before reaching the highways, you could use plug-in hybrid electric trucks, using first their internal combustion engines before reaching the highway, and then being driven electrically on the highway, and then they switch on once again the internal combustion engine after leaving the highway. This could be a first step, and once the highways are more and more electrified, these trucks could be fully electrified by having small batteries and driving the remaining kilometers before and after the highway in fully electrified mode, but using much smaller batteries. So this is a way to electrify more transport and rely less on internal combustion engine.
Okay, just quickly on that final point, small battery means short range for a truck. How much will this impact the flexibility of road transport? Because this is why you want to keep heavy duty on roads rather than put it on rails.
Exactly, and that's the positive aspect of that. In fact, the big benefit of road transport for trucks is the flexibility of the supply chain if you compare that to rail. And you keep this flexibility because, well, the truck can still drive from where you need to be supplied, then directly to the highway, possibly using the internal combustion engine or a small battery, and then it is electrified where most of the mileage is driven, and then you can supply your delivery at the supply point by using either the internal combustion engine or the battery. But it means that something like 90% of the mileage could be really electrified by using small batteries and relying less on the internal combustion engine.
Okay, this is a scenario, and there are other aspects, but we'll touch on that in the panel discussion.
Sure.
He's calling from the UK. Brief presentation. Dr. Calliope Panoutsou is a Senior Research Fellow in the Centre for Environment Policy at Imperial College London, the Chair of Biomass Availability and Supply in the European Technology and Innovation Platform for Bioenergy, and a member of the Scientific Committee of the Bio-Based Industries Joint Undertaking. Your work integrates natural sciences with economic and socio-economic approaches and policy analysis. You are currently leading research on understanding the needs for new biomass policy interventions and how these can be integrated to climate and energy policies in Green Deal in 4 Horizon 2020 projects. Calliope, I think you have a great report to tell us about biomass availability, which is critical for these low-carbon fuels. The floor is yours.
Thank you. Good afternoon, everybody. I am going to present the recent report we have prepared for Concawe on sustainable bio-feedstock availability. The report the work started in October last year and finished in June. It is an overview of the sustainable biomass availability in the European Union and the United Kingdom by 2030 and 2050. The feedstock that we assessed does not include food and feed crops. It includes only domestic feedstocks from agriculture, forestry, and waste, as they are included in Annex 9 of the Renewable Energy Directive, both in Part A and B. We have not assessed in detail, but we have included an overview of the potential for biomass imports and aquatic biomass algae based on work done before from colleagues. The assumptions for the scenarios are brought up to date and they are in line with the European Green Deal, taking into account issues having to do with biophysical restrictions of land availability, as well as the evolution of the impacts of climate change to agriculture and forestry. In all the scenarios, we have assumed that there is a strong political will to deliver the European Green Deal. We have made the assumption that COVID-19 will bring positive impacts if biomass, sustainable biomass is being developed. Because it can bring benefits to the local producers while also broadening the feedstock base. And the granularity of the report is at EU country level. And we have also addressed the low indirect land use change risk concept. And we have assessed the two types of potentials, the technically available sustainable potential for all markets, and also following, we have excluded the known demand for the bio-based materials, and we have assessed the available for bioenergy and biofuels. There is also special provision for biodiversity. There is an ongoing study that builds on ours, and we are in collaboration with the colleagues in Fraunhofer that are leading this study. They are working on detailed biodiversity assessment of specific case studies in 2 European countries, Germany and Bulgaria, as examples. So they will apply the methodology, and the aim is to have the biodiversity impact as a function of biomass provision, and try to understand sweet spots of maximum yield and least biodiversity impacts at NUTS3 regional level. The study, as I mentioned, is ongoing and is expected to be published early next year. There were three scenarios in the study. We had the low mobilization scenario, which assumes that farming practices and forest practices and waste recycling rates remain at 2020 levels. We have the medium scenario where we have improved mobilization in selected countries, and the rationale behind selecting the countries is of dual nature. We have countries that all of them that are selected in the medium scenario have high biomass potential, higher than 20 million tons per year. But there's a combination of a set of countries which have strong infrastructure. They have a good institutional framework, policy, knowledge. These are primarily countries in the northwestern part of Europe, like Germany, France, Sweden, Finland, United Kingdom, Austria, Spain. And there are countries towards the east, and like Poland, Romania, Czech Republic, Hungary, and Bulgaria, that do not have the developed infrastructure, but they do have low costs in the biomass supply. And there is a third scenario, which is a high scenario, and it has enhanced availability and improved mobilization for all the countries. The improved research and innovation issues include increased yields. They include improved practices, harvesting, management, collection, and also in terms of waste, they include the improved separation and collection of the waste fraction, of the bio-waste fraction that can be used for energy. The key assumptions, we have included a very conservative share for the available, sustainable and available unused, abandoned and degraded land. So in the low scenario, we have included the 25% of the available, of the totally available land that will be employed in the bioenergy production. For the second scenario, we have taken a 50%, and the third scenario we have taken 75%. When it comes to stem wood for energy, we have included a 25% in the low scenario, a 30% in the medium, and 50% in the high scenario. Just for reference, the estimated energetic use of stem wood nowadays is 45%. So we made sure we take into account the current debate and the future sustainability concerns for the use of stem wood for bioenergy, and we kept these levels low. And when it comes to waste, we have taken into account all the numbers of the waste directive and the recent circular economy that promote recycling. And we have fixed the ranges between the low, medium, and high scenario in a way that matches the future projections from these documents. Having performed all the analysis, we have a forecast for all markets of 392 to 533 million tons of oil equivalent per year by 2030 and 2050. And when the currently known demand for bio-based materials, bio-based products and materials is extracted, then the available biomass material for the bioenergy sector ranges from 208 to 366 million tons of oil equivalent. For agriculture, the regional distribution is closer to countries like France, Germany, Poland, Spain, Romania, while you can see that the critical assumption, which is the new biomass, which comes from the degraded, unused and abandoned land, as we mentioned, in the low scenario, we assume that only a quarter of this land is going to be brought into productivity for bioenergy and biofuel crops. For the medium scenario is a 50 and a 75 for the high scenario. For forestry, again, you can see that the issue that I mentioned, the stem wood for energy, we made sure it is kept on levels that in both scenarios, in the two scenarios, are lower than today, significantly lower in the low scenario, while there is a slight increase from today's levels in the high scenario, mainly due to improved innovation and research techniques in harvesting and processing towards 2050. And again, their main concentration of this type of raw material is in Scandinavia and North Central Europe. For bio-wastes, the potentials again have been fragmented, have been reduced to make sure they meet the guidelines of the Waste Directive and the recent circular economy documents. Important considerations. The potential is there. But it is important to highlight that biomass potential availability in this study are based on very conservative assumptions, as I tried to name. Furthermore, we have assessed feedstock that is within the Part A and Part B of Annex 9, but not all the categories. This is because not all of them have consistent statistical data sets that could fit to our methodology and modeling. So there's more potential for the feedstocks we have not assessed. Therefore, it can be concluded that the biomass potentials would most probably be higher than those estimated by this study. However, it's as all colleagues and all the recent studies that have been made for biomass supply and feedstock availability, additional research and development will be required, as well as the implementation of improved management strategies on the ground in forests and agricultural fields. Because even if the potential is there, the supply chain needs to be developed to mobilize these resources on the ground. This means that an enormous effort must be done in all member states, as the maturity and reliability of several key biomass conversion technologies is still an issue for increasing TRL levels. It's very, very important that the feedstock supply is also being developed fastly and together with the technologies. And the conclusions, the sustainable biomass availability with no impact on biodiversity. So far, there are many publications providing different ranges, and they're not always transparent assumptions. We tried within the study to compare with the studies that had open data sets and open assumptions. So the main results of the study that we have done at Imperial College is that the total potential availability ranges from 392 to 533 million tons of oil equivalent per year. If we extract the known uses for demand from the bio-based sectors, then we have 208 to 366 million tons of oil equivalent per year. We have to add here that the Clean Planet for All, the recent impact assessment of the European Commission's document, allocates 120 to 170 million tons of oil equivalent to bioenergy. So this means that the potential availability of feedstock we have estimated allows an additional 88 to 196 million tons of oil equivalent per year for biomass for the transport sector, which Concawe, as far as we know, will use these estimates to support further assessments on the potential deployment of low carbon fuels in the transport sector towards 2050. Thank you very much.
Thank you very much, Calliope, for this very interesting overview of your latest study. Before we move to our next speaker, I just have one or two short questions for you, more to come in the panel, of course. You were mentioning that you've been adapting the list of feedstock to, of course, Annex 9A and B, but the list of feedstock was a bit shorter than the full option. How have you built your shortlist?
Based only on the feedstocks that had statistical data sets of time and long time series. We have excluded specific feedstocks. There were not many, but they are still enough to have substantial potential because they were mostly industrial residues or industrial waste that we could not have consistent data or traceable data of valid quality. So we preferred to stay with data sets that are validated and statistically accepted.
So more conservative approach than assumptions. Thank you.
We thought this better than mixing ununiform sets of data.
Absolutely. The other key point, and you know this is something that comes back when it touches on biomass, is sustainability. Which criteria? So you've been giving some highlights around the biodiversity point that you've mentioned in your introduction slides. How have you been defining the different criteria for the sustainability assessment of those different feedstock?
We have added the sustainability criteria as they are within the Renewable Energy Directive. And on top of that, because the issue of biodiversity, we started last October, and the issue of biodiversity has started picking up then. So although in our study and the numbers I presented, the criteria of the Renewable Energy Directive are included, including the ones relevant to biodiversity, Concawe decided to have a more detailed focus on biodiversity, and that is why the additional study that I mentioned to you that's being performed by our colleagues in Fraunhofer, and we're collaborating, providing our data to make sure there is an understanding of which are the sweet spots of having the optimal biomass yield with the least biodiversity implications.
This looks like a very robust approach from the sustainability dimension. I will now turn to Anne Bouter in Paris for her presentation, the last one of this session before we go into the panel. And brief introduction, you are 11 years experienced research engineer specialized in environmental assessments applied to a wide range of topics. You hold an engineering degree from a top-tier engineering school in France, in Montpellier to be precise, and you're specialized also in agricultural science and environmental assessments. You've been moving to Switzerland, where you've been working on life cycle assessments, and then you joined the Economics and Technology Intelligence Department at IFPEN in January 2013 for your dual competence in life cycle assessments and biomass management. Since 2016, you have been specialized in the field of transport and mobility, and I think this is exactly what you're going to tell us about, is life cycle assessment in transport. So the floor is yours.
Thank you, Alain. Ladies and gentlemen, good afternoon. Thank you for attending this last presentation of the day. My name is Anne Bouter and I work at IFPEN. I will try to keep you interested by presenting to you the role of fuels and powertrains into the decarbonization of the transportation sector through the use of the life cycle assessment tool. I would first like to introduce my department at IFPEN, which aims at assessing the economic and environmental stakes of the energy transition. 3 studies areas make up the department. The first one is the foresight with the quantification and evaluation of energy transition scenarios. The second one is the energy markets with regulation, modeling, actor strategy, and public policies. And the last one, the environmental impacts assessments combined to technico-economic and societal feasibility. First, a short introduction to tell you that the Paris Agreement sets out objectives to limit greenhouse gas emissions in all sectors by fostering low carbon technologies. And transportation sector is brought to center stage as it accounts for almost a quarter of global CO2 emissions in 2016. Alternative fuels are a solution to decrease carbon footprint of transportation sector, as well as low carbon vehicles technologies. The market for battery electric vehicles has grown considerably, and effective public policy incentives have reinforced this perception, as they are considered as a zero tailpipe GHG emissions. To address these several solutions, life cycle assessment methodology could be very useful. Life cycle assessment is a methodology which aimed at quantifying the environmental impacts of a product or a service as part of an eco-design approach or with a view to select the optimal solution. All the potential impacts on the environment are quantified and the consumption of resources is examined, from extraction of raw materials to treatment of waste, also called from cradle to grave. It is therefore a global, multi-step and multi-criteria approach governed by ISO standards, which aims to avoid environmental impacts transfers from one stage of the life cycle to another, or from one environmental impact to another. Life cycle assessment applied to transportation sector should include both vehicles' life cycle as on the vertical axis, and also the energy vector's life cycle or also called the well-to-wheel on the horizontal axis. Yet, a brief reminder about alternative fuels, and more precisely biofuels produced from biomass. And the question could be, why biomass in transportation sector? A first answer could be that the reserves are potentially large and easily accessible, relatively homogeneously distributed, and with a good energetic ratio. A second answer is that you can also see on the slide that biomass potentially supplies almost all the different conversion pathways needed to produce alternative fuels with the light green arrows. And a third reason is that biomass can power all existing powertrains, and there is no need for technology evolvement. The diversification will depend on well-to-wheel performance in terms of energy efficiency, GHG reductions, costs, but also on the availability of resources. A few reminders about biofuels. Biofuels are incorporated in two energy pathways, diesel, in which are mainly incorporated FAME, produced with oleaginous plants, and hydrotreated vegetable oils. In gasoline pool, ethanol is the main incorporated product from sugar-rich and starch-rich plants, such as sugar beet, maize, or wheat, for example. The conventional biofuels on the top of the slide are established on an industrial scale, but are controversial as they induce potential problem of competition with food and raise the controversy surrounding their environmental performances with the indirect land use change or ILUC debate. The advanced biofuels, which include lignocellulosic biofuels, the bottom of the slide, depend on processes that are technologically more complex, but they present multiple advantages, such as a much more widely available resource, the moderate price of biomass for residues and waste, and greater environmental benefits. There are also new resources for mature technologies. At short term, the oily industrial byproducts and also co-products of the sugar and starch industry. At short, medium term, the other non-food crops as jatropha, and at longer term, microbial oils or lipidic algae. A brief presentation about life cycle assessment applied to biofuels and the scope definition related. You can see the main steps are the cultivation and the harvest of biomass, followed by the conversion, the distribution, and the use. Intermediate transport stages can be considered in between. Back to the several biofuels production pathways that I presented. The Renewable Energy Directive 2 environmental default values are presented on the graph. You can see that biofuels must meet sustainability criteria as minimum GHG savings to be eligible as biofuels. You can also notice that except for used cooking oils and animal fats, cultivation and harvesting stages, which are represented with the light green, have significant contribution to the total impact. Lignocellulosic biofuels all meet the minimum GHG savings on the top of the graph. Environmental performances are very resources dependent. The same kind of results as the slide before are presented here, but performed at IFPEN. Several powertrains propelled with several energy pathways are assessed thanks to life cycle assessment methodology. The global warming potential indicator is studied for a C-segment vehicle in 2019, performing a WLTC driving cycle. Several stages of the life cycle are presented. You can see the glider's life cycle in blue, which has roughly equivalent impacts among all the powertrains. The tire's life cycle in yellow, which have the same contribution for all C-segment vehicles. The battery's life cycle in pink has a significant contribution to the total GHG impacts for the electrified vehicles. From 4% for an HEV to 45% for an EV with a battery of 40 kWh and 55% for an EV with an extended autonomy with a battery of 60 kWh. It is noticeable also that the origin of the electricity charging mix, the green bar charts, has significant impact on the results, whether it is the French one or the European one, the lighter green. The well-to-wheel stage, and especially the tank-to-wheel stage, has significant contribution to thermic vehicles' life cycle, whereas it is rather the well-to-tank stage which contributes to biofuels impacts. As I showed on the slide before, that batteries' environmental impact has a significant contribution to the total life cycle of electrified vehicles, it seemed of high interest to have a look on this subject, especially due to the market's growth of electrified vehicles. The European Commission is expecting a 14-fold growth forecast by 2030, and thus we really need to properly assess the environmental impacts of batteries production. The answer is not so simple, as we performed a literature review on the subject, and results are very dispersed. In order to fill the gap, we performed a meta-analysis study which is submitted to a peer-reviewed journal. In the meantime, I'll present you some results for 4 lithium-ion batteries chemistries regarding the global warming potential indicator. You can see that the values range from 15 kilograms CO2 equivalent per kilowatt-hour for LMO cathode chemistry for the minimum value to 487 kilograms CO2 equivalent per kilowatt-hour for NMC cathode chemistry for the maximum value. The median value, which is the green line among all the 377 observations, is around 59.2 kilograms CO2 equivalent per kilowatt-hour. The median value for NMC observations, which is the orange line in the box plot, is 72.5 kilograms CO2 equivalent per kilowatt-hour, and the same order of magnitude is observed for LFP and LMO cathode chemistries. The median value for NCA cathode chemistry is significantly lower than the other median values at 41.7 kilograms CO2 equivalent per kilowatt-hour. However, global warming potential is not the only environmental indicator that we can study with life cycle assessment methodology. We can say that depending on the battery's chemistry and its size, BEV have lower potential environmental impacts on climate change than their thermic counterparts. But what about the other environmental indicators? If you have a look on this slide, comparing the transport over 1 kilometer with a thermic car in gray versus an electric one in green, you can observe that the electric car has greater impact than the ICE for the impacts circled in red. I would like to draw your attention, especially on the last one, the resource consumption indicator. Here is a comparison based on this environmental indicator between electric cars and ICE. The orange part represents the battery's impacts. Based on UNEP CETAC recommendations, the first approach chosen to characterize resource depletion for electric mobility is the abiotic depletion potential, or ADP, method presented here. The process contribution analysis for batteries life cycle shows that 72.3% of the impact is related to the gold. This is not surprising, as ADP indicator identified gold with the highest characterization factor. Gold comes from the use of printed wiring board to produce battery. Gold is followed by copper, silver, nickel, zinc, and tin. Lithium contribution to abiotic depletion potential indicator is less than 0.203%, and cobalt has almost no contribution to this indicator. However, it is important to consider the depletion of resources through a geopolitical risk. For this reason, a criticality indicator, also known as supply risk indicator, can be assessed. Results are generated with a technico-economical model based on times generator. This is the same kind of model which is currently used by IEA. The objective function is to minimize the entire costs of the energy system, and it is a bottom-up model. The model allows examining 2 climate scenarios, +2 degrees and +4 degrees, in order to estimate the consequences of the fast rollout of low-carbon technologies in the transport sector and how it is likely to significantly increase metals demand by 2050. The import dependency on metals of the European Union in its attempt to electrify its transport sector was evaluated in order to estimate how this dynamic could increase metals criticality for this area. This notion of criticality is often described as all the risks related to the production, use, or end-of-life management of a raw material, including geopolitical, economic, production, and environmental or social risks. Results show that the transportation sector accounts for 26.9%, 85.6%, 40.6%, and 69.8% of copper, lithium, nickel, and cobalt, respectively, for the more climate-constrained scenario, which is non-negligible. And also not shown here, but the copper and cobalt consumption in 2050, all sectors considered, will be more than 90% of the worldwide non-resources in 2010. Regarding the life cycle assessment of e-fuels, results show here that they could be very promising in terms of GHG emissions reduction. The fossil fuel comparator in Renewable Energy Directive 2 is 94 grams CO2 equivalent per megajoule as a reminder. However, the results on climate change impact are very dependent to the electricity source, as it is shown in the 2 scenarios. One called optimistic with renewable energy, and the other one called pessimistic with the European electricity mix. The main impacts come from the production of H2, depending on whether the electricity has a low carbon footprint or not. Regarding the cumulative energy demand environmental impacts, we found that driving on e-fuels is 2 to 3 times more energy intensive than other alternative pathways. To sum up, this presentation aimed at presenting the LCA tool applied to transportation sector with a focus on climate change impact. Other environmental impacts have been shown as the resource depletion potential one, and each fuels and powertrains technologies have their own advantages resumed here. For biomass, the pros are its potential abundant availability and drop-in aspects. This is counterbalanced by the potential debate of food versus fuel for some biomass sources and the question about direct land use change and indirect land use change. Another disadvantage could be the tailpipe pollutant emissions other than CO2. Regarding electric vehicles, they have a great interest in reducing tailpipe emissions to 0 and could really be a game changer for GHG reduction according to batteries weight and energetic sizing. On the other hand, batteries consume several critical raw materials, and batteries' end-of-life management is a significant leverage. E-fuels are an interesting solution depending on their production pathway, but are very energy-consuming and expensive. To conclude, life cycle assessment is a very powerful multi-criteria environmental decision support tool to guide future policies. This is a decision support tool sensitive to hypotheses, and sensitivity analysis must be performed. Large-scale scenario must also be assessed to avoid scale effect of analyzing one product. It is the diversity of low-carbon solutions which seems to be the smarter way. I thank you for your attention, and I am available to answer your question.
Thank you very much, Anne, for this very interesting presentation. Indeed, there are questions. I have some in the feed. I also have one just to the link between you now and the panel. I'm just moving to my page here, sorry. Firstly, I've seen that hydrogen is not included in the entire study. Is there a reason for that?
Yes, of course, there is a great reason. It is still under study from our side on the life cycle assessment side, but study will be released at the end of October.
Okay, so coming very soon. Good, because you know hydrogen is something which we've been discussing a lot and is part of one of the solutions for transport. So probably others would have noticed that. You mentioned in your conclusion in the pros and cons, I noted one that was the greatest uncertainty about batteries end of life, which is something that we usually don't really talk about. We stick to either tank to wheel or well to wheel discussion. You mentioned this, it could be a game changer. What do you mean exactly when you mean game changer? And if so, when could that happen?
It is very difficult to assess end-of-life impacts generally speaking, but especially for batteries, as we have a few feedbacks from the field for the end-of-life parts. And we have to collect data on end-of-life management to know from an industrial point of view how batteries are managed and which materials are recycled, for example, because there is the directive about batteries end of life, but the directive gives some mass objectives to recycle, but not quality objectives regarding the raw materials to recycle. So we don't know which materials will be recycled. And also another question remains the battery's second life, or even sometimes third life after their use for mobility usage.
Okay, I assume also we're not talking about something which is tomorrow. We need the time to come to this end of life, so probably 10 or even more years before this starts to have an effect, I assume.
It depends. You can build several scenarios to advise the trajectories for this end of life.
Okay, thank you. Let's now turn to the panel, and I will invite our technical team to bring the others on the screen. So everybody is there, and let's start with this. I have some questions. I will also include them in a discussion. My opening question is for Roland, and I'm coming back to your ERTRAC roadmap, Roland. It's, well, basically the conclusion is, as I said already, it's very tempting to see that full electrification looks as the optimal solution for road transport. From a technical and infrastructure perspective, do you believe that this is a realistic approach? And if there is some doubts about the capacity to have the energy to electrolyze, I'd say, the entire system, what would be the option or the plan B?
Yeah, let's first start with what would support the conclusion that electrification is ideal for transport. It's very simple. Electricity production decarbonizes faster than fuel production. That's the first very important aspect. And the second aspect is that, well, electricity-powered powertrains are more efficient than internal combustion engines. So, of course, the conclusion is what can be electrified should be electrified. But once you have said that, which is a very simple sentence, you have huge questions behind that. The first question is, what can be electrified exactly? And the second question is, how you electrify that? What can be electrified? Can we electrify everything? Well, the answer may be no. If we look at Anne's presentation, we see that there are constraints on the supply of minerals. We have a recent report of the International Energy Agency saying that by 2030 we would fall short of lithium and copper and also cobalt because the production is not enough. So once you have stated that you cannot electrify everything, how do you optimize your electrification? And we have released a very recent Concawe paper saying that under availability of batteries, the plug-in hybrid electric vehicles would be a masterpiece of the future fleet to minimize CO2 emissions. And in this case, it means that you still have internal combustion engines to drive part of your mileage, which means that you will rely on fuels finally, which also need to be decarbonized.
Okay, so two points that I take away. The first one is if we add the LCA dimension to the ERTRAC roadmap, it changes, or it could influence some of the conclusions, meaning the full electrification scenario is not necessarily the best option, or at least can be challenged. And the second option is this brings liquid fuels back in the discussion.
What we have not taken into account, considered in our roadmap, is the feasibility of the scenarios. Maybe they are not feasible, and in this case, the optimal scenario is a different one, indeed.
Okay, so we're really into a theoretical approach in this. Okay, very good. When it comes to the other aspects, because when we talk life cycle, and I'm looking at Anne again here, when we talk life cycle, you've added this environmental dimension, and I found this very interesting graph where you've shown a comparison between electric vehicles and ICEs with regards to various aspects. You gave a focus on the depletion, the risk of depletion. On the other aspects, there is a very little difference between the two technologies. So my question would be, given that from where we are today, the diesel technology seems to be a mature technology. Bob might challenge me on that one, saying that there are still rooms for improvement, and happy to bring you in the conversation. How much do you see an improvement capacity for the electric vehicle from an environmental perspective?
It's very hard to say because depending on the battery, if you increase the battery's autonomy, in the meantime you increase the battery's weight, except if there is great progress for batteries technology. And if you increase the battery's weight, you need more electricity consumption to propel your vehicle. So it's really the interesting thing with the life cycle assessment. It is that you can assess in its entire life cycle the product or the service that you want to assess, and the answer is not trivial actually.
Okay, so Bob, is there still room for improvement from the diesel side then?
Well, certainly I think there is some room for improvement, as we discussed about using technologies like ducted fuel injection. When we talk to the heavy duty diesel engine OEMs in the United States, they're pursuing some other technologies as well, like engines that are capable of higher operating pressures and higher pressure rise rates that would operate more efficiently. Although I think those improvements are going to be marginal, like 1 or 2% or so in efficiency, which is significant for a large truck operator, but not of a gigantic magnitude, obviously. I think the major improvements can occur in reducing the tailpipe air pollutant emissions impacts of diesel engines.
Okay. In terms of quantity, if we were to have this approach with a rather broader PHEV approach for heavy duty, are we still on track with the biomass availability that has been mentioned by Calliope? So somewhere around, I'm just taking the numbers back, I noted them here, 88 and 196. So even if we take a median there, somewhere in the middle, in 150 million tons. And to be clear, I have the question. This is, how do we translate that into fuels, by the way, Calliope?
Thank you for the question. We have the study itself includes a very detailed assessment of translating the specific feedstocks into advanced fuel carriers. So don't have all the numbers into detail, but there is enough biofuel coming out in the end. But I would suggest to have a look into the detailed pathways within the chain.
Okay, but at least from a sustainable fuel perspective, that should be still in line to cover the potential contribution to heavy-duty transport.
Yes, it is.
There is a question back for you, Roland, to the roadmap again. How can the results of this study be extrapolated and applied beyond the EU? Is there a limit in scalability? That's a tough one.
That's a difficult question. Well, the question here is about the feasibility of the scenarios. In Europe, we know that the electricity system is deemed to decarbonize quickly, and so we have made this assumption that the system can decarbonize quickly. Can we make similar assumptions for the electricity system in China? We're currently relying a lot on coal power plants. I'm not sure. So the question is really about the realism of the scenario that we have drafted, and whether it can be expanded to other areas in the world, relying more on fossil fuels for electricity production. I don't know if it's realistic.
Okay, plus this also increases, I assume, the metals, labor, resources, etc. that is required. That's an element to take in consideration, so I understand very difficult. When it comes to e-fuels, because you underline the little efficiency of transforming electricity into e-fuels, whereas e-fuels is something which is really seen as one of the big opportunities when it comes to either aviation or even road transport. Do we have to look at e-fuels only from a European perspective? Can we consider perhaps also the production of e-fuels in regions where the electricity demand is not as high as what the production can enable, meaning that it doesn't become a transformation just for the benefit of e-fuel, but a way to store electricity, and this can then be used afterwards through what we would call just markets brought back to Europe. So is this not a way ultimately to address this challenge of efficiency?
Well, it's at least a way to secure our energy supply, because liquid fuels can be stored very easily. So whether you do that by using liquid fuels and bringing them to Europe or to the user is the first way to do it. Another way which can be considered is to store hydrogen and not to transform it, and then to put it back in the electricity grid by using fuel cells. So you go back and forth in the electricity system without entering the liquid aspect and internal combustion engines. You have many options that can be considered.
Okay. There is one question, but I do have a little challenge here on an acronym, so maybe you can help me. I don't like to put acronyms which I don't understand. JWP.
Global warming potential.
Okay, so now I can put it. It's a question for you, Anne. At present, there is a lot of discussion regarding the global warming potential for crude oil extraction, with some sources suggesting that the CO2 impact is a factor from 3 to 5 times higher than generally used in LCA modeling, the reason being attributed to methane venting. The baseline for global warming potential, thanks, for crude oil extraction would be substantially higher than currently used in models. Would this change your conclusions?
Thank you for the question. I am not aware of such work, but of course, with a scale factor of 3 to 4 for the well-to-tank stage for fossil fuel, knowing that gasoline and diesel are around 14 grams of CO2 equivalent per megajoule for this well-to-tank stage. It will drive the fossil fuels much more higher than presented here, only for the well-to-tank stage, because it would have no impact on the combustion stage. So yes, but it will also go in the same way for the conclusion, I think, because we would definitely have the alternative pathways with lower GHG emissions at the end.
Thank you. I think indeed it's good. It's a small share ultimately in the entire cycle, so the influence shouldn't be that big, should it, compared to the combustion part?
No, it will be bigger, but not as big as the combustion part.
Robert, you've been mentioning in your presentation that you had identified about 12 high potential compounds. If you were to highlight 1, 2, or 3 that are the most promising or have the highest potential for plug-in hybrid, what would be your selection?
Well, I'm not sure that my choice would be different for plug-in hybrid versus just ICE. I think it would probably be the same, at least at this point. I think if you look at a combination of life cycle greenhouse gas emission reductions and potential modeled cost, technologies such as hydrothermal liquefaction seem to have really high potential. They're at a low technology level or moderate technology level today, would require significant development. And then while at a very high level of technology development, fischer-tropsch fuels from biomass also seem to be very favorable from a greenhouse gas emission reduction perspective, although capital cost is, of course, very high for these processes. So I think I would highlight those as really having large potential for large volumes of economically viable low carbon fuel.
Well, that's already a good indication, and indeed, ultimately, it's a combustion engine, be it with the plug-in or alone. It remains the same technology from a combustion perspective. I have some other questions joining, and one is for you, Roland. It's about the roadmap again, and this idea of having electrified roads. The question is whether these would be with catenary or in-road charging system.
In fact, in our roadmap, both options are considered, and there is a kind of fight between the two suppliers which want to define the standard for that. Well, both are possible. They have their benefits and drawbacks. Well, among the drawbacks for the in-road system is that it is more difficult to implement, and it is more difficult to maintain the road because bitumen can be damaged around the road. For the overhead catenary system, you may have more issues with safety and materials which can be stolen. This is also important when you consider infrastructures. But for the moment, the decision is not made.
No, I imagine. Practically, do you associate passenger cars on the same roads, or do you have separate lanes? How does it work?
For the moment, it's not an option which is considered.
Okay, so it's really specific lanes, traffic lanes.
Yeah, I think you need to have specific driving skills, either because you need to remain on a lane, or you need to care about your overhead catenary. So it's not for every driver, and it's really dedicated to heavy-duty drivers.
Okay. Bob, back to you. Yesterday we had some conversation around HTL, and HTL was shown as a very early technology which had still quite some way to go before becoming ready or close to technology readiness, at least at the highest rates. I have the impression from your presentation that HTL is more advanced. Is this right, or am I wrong?
I don't think it's been practiced on a really significant scale, like larger than larger than a ton a day, for example. So I think there's a lot of development to be done there. It's just that all of the indications are so promising from the process simulation, the techno-economic analysis. But certainly it's not a fuel that I think could be a full-scale biomass conversion process within a year or two. It's going to take a little longer than that.
Okay. We're getting close. I have been looking for last or final questions. I would like maybe to close on just a conclusion question. I'm just checking one last time, but indeed, I think we came to an end from that perspective. My last question would be, currently we know that when we look into the policy part, I'm not going to talk policy, but I'm going to talk realism in the way we want to assess. The policy doesn't look at LCA for various reasons, in particular the methodology, the uncertainties, the difference of views, and probably different approaches depending on from where you come. If we wanted to have a fair assessment of all those technologies, can we live with a well-to-wheel? I don't even mention tank-to-wheel. Can we live with a well-to-wheel, or is it absolutely necessary to move to an LCA? And I'll start with you, Anne.
Thank you, Alain, for the question. As I presented at the beginning of my presentation, regarding the evolution of the transportation sector, and especially the electrification of the transportation sector, it is absolutely necessary to take into account the global life cycle with the life cycle assessment methodology. And it was the graph I presented with on the vertical axis the vehicle's life cycle, as I showed that batteries can have great impact on the global warming potential indicator. And you must also consider the well-to-wheel assessment of the energetic pathway, of course. But you cannot, from my point of view, it is not fair to exclude the vehicle's life cycle and not take into account the vehicle and especially the battery for electrified vehicles.
Thank you, Anne, for that conclusion. Calliope, to you, when you did the study on biomass, of course, you also had, in a way, an eye on the full life cycle, because we were talking about sustainable biomass from the very beginning. So would it make sense to you that we do have such an approach for biomass and we only stick to well-to-wheel for other technologies?
For me, it is all a matter of giving a fair play to all. So if biomass has more analysis in certain elements, of course it's a diverse raw material, difficult value chains, etc. But I think it will be more clear, and it will be more fair to have the consistent comparative approach for all, and not only for biomass.
Thank you, Calliope. Robert, what's your view in the US?
Well, in the US, there's sort of a complicated mix of policies and regulations. The Renewable Fuel Standard and the California Low Carbon Fuel Standard both require blending of certain volumes of fuels that achieve a certain level of life cycle greenhouse gas emissions, and they define a process for making that assessment that many experts in life cycle analysis may not fully agree with, but at least it's a consistent process that everyone has to use. But at the same time, the diesel engine manufacturers are required to meet a tank-to-wheel CO2 emission standard, which is essentially an efficiency standard. But at the same time, if they were to make a lot of changes to their technology to be able to utilize fuels that are not drop-in fuels because of their low carbon intensity, they would get no credit for it within the regulatory or policy framework. But my opinion is that life cycle emissions, or life cycle analysis as a part of the policy is really the key to decarbonizing transportation. I don't think you get there without it.
Thank you. And I'll leave the closing word to Roland.
Well, definitely, if you want a fair picture, you need to move to life cycle assessment. But I would even say that it's not enough now. In fact, life cycle assessment does not take into account systemic effects. And it's, in general, you have a back-to-back comparison of one electric vehicle versus one internal combustion engine or hybrid vehicle, whatever it is. But it's one thing to compare one thing to another, but it will be different if you compare 1 billion cars to another 1 billion different cars. And if we want to think at the system level, if we want to change the system, we have to think at the system level. And this is where the different constraints will appear in terms of critical minerals, availability of renewable electricity, and so on. And this is where we will find, in realistic conditions, the optimal solution.
Thank you very much. Let me conclude here this fourth and final session of the 14th Concawe Symposium. We've been hearing about life cycle, and we've heard the importance of that, firstly to compare in a fair way all technologies. We've also heard that biomass will be available, at least at EU level, with regards to the amounts that have been scenarized in several potential pathways, and there is a positive response for that. We also heard that there is still some improvements in terms of molecules for the diesel technology, and these can be very helpful when it comes to heavy duty. And finally, we've heard that theoretically there is an electric pathway that seems to be rolling ahead of us, but when we add all the dimensions that we just mentioned, this can be put in question and discussed, and we have to assess where it really has an added value. With this, I thank you all. It is the end of the session,